So welcome to the fourth lecture of the logic and set theory. In this course, in this lecture, we will talk about the refutation trees. So in this lecture, refutation trees and valid arguments, refutation tree rules will be discussed here. So we will learn about that topic and remind you about the home page. So there are some references. The first one is Richard Jeffrey, Formal Logic, and there are other books here. Also, there was some course in MIT, so you should look at something similar to this, which is called the Search for Counterexample Test for Validity. So refutation tree and the valid argument. So recall what valid argument is from the previous lecture. So we were given some premises, and we want to show that conclusion is true always. Okay. So first we negate the conclusion, and we show that the premises and the negated conclusion cannot be all true at the same time. So if you have a premises all true, then the conclusion cannot be false. Okay, so that's what we are trying to show. So this means that so if you succeed in doing this, then this is the valid argument. Okay? So this is the method that we'll be using. So if premises and the negated conclusion are true in some way, then the argument is false. Okay, so if you have every premise is true, but the conclusion is false for at least one case, then of course that's the counterexample to our conclusion of our argument. So therefore, the argument is invalid. Okay. So that's how. So I have to probably justify what I'm saying, but we will just at this stage we will just go over and what I'm saying as the truth. Okay, here. So refutation tree example. So we break down the statement into atomic pieces and see if there can be all true instances or not. Okay, so the aim is to obtain a path of atomic statements that holds at the same time. So for example, if you want to show that P and Q imply P, okay. So to verify that, we say P and Q and not P. So so let's see. So we say that P and Q. So this is equivalent to saying P and Q is equivalent. So we can break this into P and Q, but they are holding at the same time. So we have these P and Q and not P. So that cannot be all true because we have P and not P contradicting each other. Okay? So this is a valid argument. Okay? So now we check next example. So P or Q, then and not P imply Q. Okay, so we want to show if this is a valid argument or not. So we check P or Q, and so we first say not Q. Okay, so P or Q, not P, and not Q. Okay, so we want to check whether this is valid. Okay, it can be all true. There's for all true instances. Okay, so we can check this, and we want to split into two parts, where P holds or where Q holds. Okay. So we see that there are two possibilities. So not P, not Q, and P hold, and not P, not Q, and Q hold. Okay. So in either of the, so there's two branches here, two passes of branches. So we see that not P and P contradict each other, so it can't be true, so we put X here. Not P, not Q, and Q, so these two are contradictions, so we put X here. Okay. So in either of these two cases, these cannot all be true. So this is a valid argument. Okay, so that's how we check this validity of this case. So there are these reputation tree rules. Okay, so if you have a negation of some sentences, then any open path contains both formula and its negation, then we place X. So this path cannot hold. Okay, so as we did in example, if you have a negation in any open path, so we check any unchecked negate psi, and we just write this psi at the bottom of each path containing it. Okay, so you have to repeat it for every path you had. So of course in this case we have to just close the path. Okay. So in conjunction case, then we check any psi and phi and psi, and we write phi and psi at the bottom of every path containing it. So you write it in a vertical way. Okay. So if you have any disjunction, then so for any unchecked phi and psi, we check it and split the bottom of every path into one where this psi is added and where this phi is added and where this psi is added. Okay, so we split into two. So next we have a conditional. When you have an unchecked phi implies psi, we check it and branch every path into two parts. That's one is not phi and two is phi. So this is because that essentially the this statement is equivalent to not phi or psi as in the logical sense. So we are using this rule here, disjunction rule here. So by conditional, so if you have psi equivalent to phi, then we branch everything into two parts where these hold at the same time, not phi and not psi, and psi, phi and psi. Okay, so these will hold at the same time. So we write it in the particular manner here. So again, we have to show this is a rational thing to do, but I am skipping this step. So path is finished when X appears. So we cannot add anything more. Okay. So when every path gets closed, then the argument is spotted. And if some path does not get finished, then of course this is invalid argument, and you can check, you can find the counterexample there. Okay. So we continue with the reputation tree rule. So this is sort of a derived reputation tree rules. So actually you just need to know this part only, but we continue with this one. So negated conjunction, so you take a negation of phi and psi, we check it and split bottom of every path containing into two. So one is not phi and not psi. Okay, so this is again because of this equivalence. So you have a not and psi. So this is actually equivalent to not p or not phi. So that's why we are using a disjunction rule here. So negated disjunction. So when you have a negation of phi or psi, then we write not phi and not psi and in a particular way. Okay, so you just write it in the particular way. So as you know, the particular just means it will hold at the same time. So negated conditional, not conditional is in every open path, and check any unchecked psi imply phi, and rewrite phi and not phi in the bottom of every path containing it, so it's in the same path. Again, this is because you can write this as not phi or psi here, and of course that's equivalent to psi and not phi here. Okay, so that's why we're doing this. Okay, so negative biconditional, so in every open path we check any unchecked psi phi, and we branch the bottom of every path containing into 2 and write psi and not phi and not psi at 1, and then write not phi and psi at 2. Okay, again I can show why we are doing this, but we will skip this step. Okay, so so this is the first part of the lecture. We will continue with the examples